All right. So I think for future classes, I have a webcam I'm going to start trying to use that hopefully will record the audio a little bit better. But hopefully you're in here in class, so you shouldn't rely on that recorded lecture. So we'll kind of pick up where we left off. I'll kind of mention some of the things I mentioned on Tuesday. We'll kind of restart looking at state a little bit. So if any of you guys are having issues, one thing that I worked with a student on, and I put up an additional Word document for is how to get this downloaded on a tablet. So it works a little bit different. Also, if you're on your laptop, the way that I showed you how to use it in class will work for any university computer, which is why I show you how to do it that way. I can't actually download the program, which is Citrix, which is kind of what I'm working through this web browser on. It's a little bit more seamless if you actually download Citrix and then kind of go to that app on your computer. So it's like instead of using Microsoft Word from here, you're actually using the downloaded version of Microsoft Word. It's the same idea. Instead of using the Citrix Workspace app to access data through a web browser, you can actually open it up on your own device. And that usually makes it a little bit easier. So if you're having any issues or difficulties, I had a couple people stop by during office hours yesterday. That's a great time to get some help. Because after class today, later, excuse me, this afternoon, I'll probably get that first problem set posted. We won't have covered everything so that you can't like work through the whole thing and complete it yet. But at least some of the first few questions, it's stuff that we should have covered today. You can kind of start working on it early. Don't come to me the day before that assignment is due and say, I can't get stated to work. You should be doing that this week prior to us. I mean, hopefully you've already got it going. If not, definitely prior to kind of next week, us starting class on Tuesday. So I'll put an announcement on the Canvas. I should be around a little bit tomorrow, just with some hours. If you need some additional help, kind of like some additional office hours, and you could stop by. I'm likely going to have to, I am not going to have office hours on Monday because of Martin Luther King Day. Kind of the university is off. I'll redistribute those hours to next Wednesday and Friday. So I'll still have the same number. They'll just be a little bit different next week. Okay. Other than that, we're still going to be kind of picking up where we left off on this week 1 slides file. I'm also going to be using that stated due file, review of statistics, and we're going to be using those same kind of 2 data sets. Okay. I don't think we'll progress to week 2 here. If I do, in fact, I can just publish this right now. So we have access to those if we get that far. I don't think we're going to, but just in case we gotta have those available. So before we jump into material here, we don't really have anything that's due. I won't start using those in-class quizzes until next week. Any questions for me before we kind of dive into things? Okay. All right. So we kind of left off last class. We started talking about a little bit of review of what you hopefully had in your statistics course, which is measures of central tendency of a variable, right, or a data set. So this is things like the mean. We talked about how we calculate the mean, the median, kind of it's not subject to or it's not influenced as much by extremely high values. And then we said the mode was just the value that happens most often. We'll have ways to kind of identify these in Stata that we'll look at today. So usually we'll kind of talk through these different variables and then we'll see how do we get them from Stata. Right? We also talked about the variance and kind of scaling that variance by taking the square root gives us a standard deviation. That's going to tell us something about, okay, we know the mean of this data set is, or the central tendency is here, but we could have the same mean and much more variation in the data, right? And so what that's going to look like, we'll kind of take a look at Stata once again for some specific variables, see how we can get this from that program. So if instead, I kind of glossed over this last class, but let's say instead of just calculating the mean of a normal data set, and we'll start working a little bit more of this next week, but we have something like grouped data, right? If I just had every single individual's GPA in this room, how would I find the mean? Simply add up everybody's GPA and divide by the number of students or people in this classroom, right? Let's instead say I only have the GPA of students by, I don't know, everyone's pretty much an econ major here. So let's say by what their specific classification is. So I can see for every first semester junior, every second semester junior, every first semester senior, every second semester senior, I have grouped data, right? So I know if I'm selecting something at random, there's a certain probability they come from specific groups. And then for that group, I know the average GPA. So here I've got just kind of a random variable, y. I know it could be the different values from 0 to 12. Okay? This doesn't really apply to my GPA example, but you kind of just to kind of start out thinking about this. And that every single value I know has different probabilities of occurring, right? So I know that if I selected a person at random, the likelihood that I see a 0 is 0. There's no chance I could see a 0 here, right? Maybe this is like the number of months that someone, runs a deficit with their credit card or something like that, doesn't pay it off. I know that if I selected someone at random, the probability that I see a 3 out of the 12 months would be 0.2, so on and so forth. So if that's the idea, how would I calculate a mean here? So when we're calculating means, if we have a bunch of different observations, so here I kind of had, observations, a bunch of different values I could see this observation take on. I have 0, 1, 2, 3, all the way down, right? I then have different probabilities of seeing that variable take on certain values. So the probability it had a 0 was 0. The probability it had a 1 was what? 0.06, 0.03, 0.2, 0.2, etc. Okay. Well, I can't simply add these values up and divide by the number of values I have to calculate the mean because some values happen more often than others, right? So how would I calculate the mean here? Kind of our general form of our equation. We said we're going to, when it used to using the summation sign. So add up from the very first value I could see YB all the way to the very last possible value. Usually this would be like the number of observations, where you think about here, we're going from really 1 to 12 here. Oh, it cut me off because I'm accidentally on a different page, right? So I would go through every single possible value that Y could be, and I would then multiply it by the probability I see this random value, this random variable of Y take on that value. So really what I would do is create an additional column. If I had like Excel, this would be pretty easy, right? I take Y times the probability I see Y take on that value. So for this first one, it would just be 0 times 0 is 0. 1 times 0.06 is 0.06. 2 times 0.03, 0.06. 3 times 0.2, that's going to be what? 0.6 if I'm doing math in my head correct. I would then kind of continue to do that for every single possible value I have. I would then add all those values up. Now, usually to calculate a mean, if this wasn't kind of grouped by different specific values, we said we would divide by the number of numbers I have. But because I'm factoring in these probabilities, instead of dividing by the number of numbers I have, I'm actually dividing by the sum of all these probabilities. If I've looked at every single possible value this variable could be, what should the probabilities always add up to? 1, right? It's 100% of the possible values you could take. A lot of times in this class, we're going to go from like probabilities to percentages. So if I talk in terms of probabilities, a probability of 1 would be what as a percent? 100, right? All you're doing to get to a percentage is taking a probability and multiplying it by 100. Or if I said this was 100% of the data, you know that the probability is 1, okay? So essentially, I can ignore this denominator when I'm calculating the mean using kind of group data, right? Or kind of that has associated probabilities with seeing different values. Because I know that this numerator, hopefully, if I've done things correct, should always be 1, okay? Is this looking somewhat familiar? Hope we've talked about this a little bit. Now, if I wanted to calculate a variance doing a very similar thing, so usually our variance, we said, we would add up the deviations of every single observation from the mean of that Y variable, square those deviations, and then divide by the number of observations that we had, okay? If I'm doing it this way, well, now when I'm calculating the variance, I'm still going to be adding up, but now it's what was this value I could see Y take on, what was its deviation from the mean squared, but how likely is it that I see that deviation from the mean? Well, that's where I now multiply it by the probability I saw Y take on that specific value. And then once again, similar to the mean, my denominator is no longer n. It's the sum of those probabilities, which should always be 1. So once again, I'm just kind of left with the numerator there. So in this specific example, if I were to write this out, what would I do? I don't remember. We could do it real quick. So if I take these, and this is where we'll do this kind of quick. We won't be using Excel a lot, but I could be doing this as on a calculator. Hopefully we'll start to see things like Excel make life easier. State is going to make, my life even easier. So I just want to copy these values, right? So what was I doing when I was calculating the mean? I was taking y and multiplying it by that probability. So the value of y times the value of that probability. Okay? I could then do that for every single observation. I then wanted to add all those up. Once again, I'm not going to be expecting you to use Excel. You don't have to. You could do this by hand, but Excel would make it a lot easier. And hopefully once we get to Stata, we'll see it's even easier, right? So the mean here I've got is 5.12. Okay. So I've now got, I've now got the mean is 5.12. So what would I do? I'm going to go through every observation and find that deviation from the mean. All right. So for the first value, it would be what? 0 minus 5.12. I then square that deviation. We said, what does that do? Anytime I square a number, it becomes positive. So I don't care which side of the mean it's on. But then also squaring it is going to overpenalize what? Extremely high or low values, or extremely large deviations from the mean. So here I'm going to square that deviation from the mean, but now I have to multiply it by the probability I saw that. Well, here, will I ever see a 0? No. So is this value actually going to influence my variance? No, because it's never going to occur. Now, when I go to the next possible value for y, well, that deviation from the mean, what's the likelihood I see a value of 1? 0.06 or a 6% chance. So there is a likelihood I do see that deviation from the mean, and I'm multiplying that by the likelihood or the probability I do see that deviation. I would then kind of go through, do this for every single possible value. That would give me my variance, right? So I could do kind of a very similar thing. Instead of doing this all by hand using a calculator, right? I could say, okay, take this y value, subtract, and here I'll get a little bit tricky, but here's the mean. I want to freeze this cell reference. I could have just typed in 5.12 here, but I'll show you maybe why I wouldn't want to. I'll square it and then multiply that by probability I saw that value. Okay. Once again, we could do all this by hand in the calculator. It's just now we have all those deviations squared times their probability. I can now add all of those up. And it's a weird example, but I get a variance that's about 5.4. So if I compare this to a different data set, let's just for a second, before I change this, we know the variance is 5.4. Let's say I change this to 0.07. And then the remaining 0.04 gets added to these two values. What is that new data going to have? Well, if I now can actually see the values of 10 and 11, there should be more variation in that data set. Because now when I add in those deviations from the mean, they're going to get multiplied by a probability that is not 0. So if I go ahead and change this and redistribute those probabilities, I should end up with a variance that is now higher, because the variance is a measure of how much variation there is in the values that I'm seeing. And it's now not a probability of 0, I see 10 and 11. There is an actual probability associated with that. Right? So, excuse me, this is how we can calculate variances if we just kind of have the observations and associated probabilities, as opposed to just having every individual, y value for whatever variable we're looking at. Okay. So once again, hopefully this looks somewhat familiar to what you did in your stats class. We'll kind of be reusing this throughout the semester, how we calculate means and variances, not just of an entire data set, but if that data set is kind of grouped and we only have the probabilities of seeing certain values. So for example, I was using this in my B251, but if you go out to like the Bureau of Labor Statistics, you can't get every single worker's salary, right? It's not possible. but you can get it. Well, how many workers fell within this range? So I know that the likelihood that they had between 30 and 40,000, or maybe it's even more fine, 30 and 32,000, the probability was 0.025. So I might be able to get the data that's kind of grouped as opposed to individual level data, in which case I would have to calculate my mean and variance this way instead. If I can get the individual level data, we just go back to you would usually think about calculating mean and variance. And in fact, most of the data sets we work with, we're going to have individual level data, so it makes our life a lot easier. Okay. But just kind of revisiting some of these things that hopefully you've seen in your stats course before. Now, I know I went through this kind of Excel example kind of quick. In fact, I'll save this and just drag it onto where I want. And I want to put it on this PC, make sure I have this for later, so I can put it onto Canvas for you if you want to go back and look at it. I'll know what that means later, okay? Any questions on that before we keep moving? Once again, won't typically use Excel after probably this week very much, other than to make some really quick calculations that I don't want to do by hand using a calculator. So we went through this example. Let's move Zoom's little toolbar kind of out of our way. Some other measures that we have, and I don't know if you talked about these in your stats course. Once again, everyone has kind of different background. Even though there's equivalent stat courses, they all cover things a little bit differently. But we not only have kind of our first, what we would call moment of the data. So that's the mean, the median, the mode. We have the second moment, which is the variance. We also have the third moment, which is we call skewness, right? So skewness, basically, this looks very similar to what we would kind of be doing with a variance in the numerator, right? I'm taking the y value, subtracting the mean, but instead of squaring it, I'm cubing it. So now I could actually have positive and negative values, right? So if there's skewness, essentially what skewness is representing is that, yes, I've got deviation from that mean, but there's more deviation on the left side versus the right side of the distribution. And also when I cube it, if squaring it over penalized extremely high or low values, what is cubing it going to do? Penalize it even more, right? Because now you think about it, 1 times 1 times 1 is 1. 2 times 2 times 2 is now 8, right? So it becomes an even larger value that gets added to that numerator. So we won't actually go through and calculate skewness by hand. I'll show you later today how we can get that from Stata though. And then we've got kurtosis measures. Once again, we won't focus on this a ton, but it's basically going to be a measure of how what we call fat our tails are, right? How much of the data kind of is extremely varied from that mean. So when we think about distributions, here's the different possible values I could see this variable take on. What is on my y-axis? So if I think about if this was a y variable, and let's say this value is 50. When I go up to my distribution, that tells me how many times 50 was happening out of the entire data set. So what would my y-axis actually be? It's the number of times something happens. Out of the total, it represents 5 out of 50 students are 19 years old. That would represent the probability that if I selected someone at random, they're 19 years old. So all a distribution tells us is for all of these different x values, if I go up to that distribution, that's the probability. If I selected one observation at random, that's the probability is equal to that x value. So if we're thinking about anytime I'm showing these distributions, if the axes aren't labeled real specifically, they should always be. Anytime we're looking at a distribution of data, you can think of it as whatever this y variable is, these are the different values for y. What's on my y-axis? It's the probability that if I select a person at random, that variable is equal to that specific value. So our y-axis always represents probabilities. Okay? So if I was looking at a data set and it had a distribution that looked like this, what value would have the highest probability associated with it? Whatever this value would end up being, right? And then is this value more or less likely than this value? So is it going to have a higher or lower probability? Higher, right? That's all the distribution is telling us is what's the likelihood of seeing these different values for this variable y. So we'll depict these distributions quite often in graphs that look like this. And once again, we won't use the value of kurtosis a lot in this class, but we'll see how we could get this from state, and it has more uses if you were to take like a higher level econometrics or stats course. So we kind of already started to introduce data last class. I want to go through a little bit more before we kind of jump back into it. I try not to kind of bounce back and forth too much between material and state. I try to kind of keep them, spend more time on each one and not kind of continuously jump back and forth. So we want to talk about a couple things before we kind of jump into it. So anytime we have two variables, each variable has its own distribution, right? But we also could have joint distribution. So if I think about our end goal in this class, I said on Tuesday, is we want to know like causal relationships. How does X influencing Y? Okay. So if I had something like class size and math scores, I might be concerned that in larger classes, students are more likely to get lost and they're not actually performing as well. Whereas smaller classes, I can give each student more individualized attention, and that actually improves their performance. Okay? So if these are my two variables, I might be interested in how they're correlating. So before we get to correlations, we need to talk about a specific measure, which is the covariance. Okay? So the covariance, it looks kind of like our variance, although it's not squared. It actually kind of looks like a standard deviation. But instead of just writing sigma and then whatever variable we're looking at, we write sigma and both of the variables. So what this is our covariance between X and Y. So what the covariance is going to pick up is that when X happens to be on one side of the mean, what side of the mean does Y tend to be on? So let's kind of do this thought experiment and think through this, all right? So I'll use some kind of shorthand here as opposed to just saying it in words that I think will help make a little bit more sense. So if I'm looking at this covariance, I said it's the sum of deviation of each observation. So starting with the first, going to the very last observation, and we'll do population data here. So the deviation of every observation's value from the mean of X times the deviation of every value for the Y variable from Y's mean, right? So I think here we had like what? X was class size, and here we had kind of math scores, okay? So what I would go through and do is say, okay, look, maybe this had a class size of 20, and the math scores on some, I-step test or whatever it happens to be was, I don't know, 300. Let's say I tell you that the mean class size was, I don't know, 30, and the mean math score was 350. Okay. So for this one observation, right, what side of the mean is class size on? Is it above or below the mean? Answer this question, we're going to have a long semester, right? So if class size is 20 and the mean is 30, what would the difference between this value for class size be and the mean? It's going to be negative, right? So I've got a negative value. If I'm looking at the math score, is it above or below the mean? 300 is less than 350, so that difference is going to also be negative. When I multiply a negative value times a negative value, what am I going to end up with? A negative value. So this is kind of like I'm representing what the sign for that observation's value is going to be that we add into the numerator. Yeah, so I take this difference. I guess I can add in here. It's kind of implied when we have this, but I'm multiplying it by this difference. So if I wrote negative. If I have a negative times a negative, that should give me a positive value. Sorry. If I had a different observation, let's say this one was 25, and this happens to be 370. Well, what side of the mean is class size on? It's below, so I'd have a negative difference there. Now what is the math score? It's above, so now I end up with, when I multiply those, a negative value. So this one observation was evidence that these two variables happen to be on the same side of the mean, right? That they both were below. So that's evidence that when class size is lower than the average, math scores tend to be lower than the average. This observation was evidence that when class size is low, below the mean, math scores actually tend to be higher, right? Now, I could go through this for every single combination, right? Maybe I end up here with 40, 320. Class size is now above the mean. Math scores are now below. This would be evidence that these two variables tend to be on different sides of the mean. Now, I would do this for... So yes, sometimes, you'll have class sizes that are below the mean and the math score ends up also being below the mean. Sometimes you'll have an observation where class size is below the mean, but the math score is above. Well, if I add these up across every single observation, essentially what this is telling me, the covariance is saying, on average, do these two variables tend to be on the same side of the mean or on different sides? All right, let's repeat it. Oh, that's not good. So I contacted them about this because it was going out on my desktop here. So let's see, device will not be less connected. Let's see if this to work real quick. Move my mouse a little bit. So I think they've got some settings that I can't alter because I'm not an admin on this computer, and I think it's timing things out for us in this classroom. Once again, I called yesterday. Oh, of course, this isn't. Let's see if we can get this. Okay, I might have to start hitting buttons on this to wake it up. I've never had counted this problem before. Should be working correctly. There we go. Now we're back on. All right. So the covariance, like I said, in a less technical way, you can think about what is it measuring. On average, do these two variables tend to be on the same or opposite sides of the mean? If they're on the same side, so I end up with a covariance that is positive, that is saying that when X is higher, then Y also tends to be higher. So a positive covariance here would tell me that when class sizes are larger, math scores actually tend to go up. That probably is counterintuitive to what we know, which is it's probably more likely that that covariance is negative, which means as my X variable goes up, my Y variable tends to be lower. That when class sizes get larger, performance on whatever test is measuring that class's content tend to be a little bit lower. Each student is getting less individualized attention, et cetera. Okay. But I think sometimes seeing it this way can kind of help us remember what that covariance is measuring. Okay. Now, one problem with the covariance is if I'm looking at a variable, so like class size, what's the units of class size? The number of students. What's the math score unit? Points on the test. What would I have with the covariance? What's the units? Student times points. What is a student point? Right? These units don't really mean anything. So what we'll end up doing with these covariances is first, and there's another reason why we would do this, but we're going to divide by the standard deviation of both variables to just account for how much variation exists in those variables. But also, if I divide student times points by student times points, what's the unit of my covariance? Unitless. So I now can compare the covariance between class size and math scores to maybe the covariance between hours studied and those math scores. I can compare the relationship between any two variables because it's a unitless measure. I can't compare the variance in test scores on a math test score to the variance in human height. They're completely different units, right? But with a covariance, it's a unitless measure of the relationship between two variables. So if I have a covariance of 10 between class size and math scores, and I had a covariance of 20 between the hours studied and math scores, which of those variables is influencing math scores more? Well, if it's a unitless measure, a higher value would represent a stronger positive correlation or covariance relationship. So that covariance of 20 would tell me hours studied in math score, there's a stronger relationship there than there is between class size and math scores, right? And if I'm really worried about student performance, that means where should I be devoting my energy and resources? Not as much towards class size and more towards trying to get students to study more, right? And you could use a bunch of different examples to get at this, but this is why the covariance is nice. Sorry, I shouldn't say the covariance is nice. The covariance is difficult because it still has those units attached to it. When we scale it by dividing by the standard deviation, now we've got this nice unitless measure. So what allows us to compare across data sets is not the covariance. We need the covariance to do this, but we'll scale the covariance by the standard deviations, which gives us what we call the correlation coefficient. This is our unitless measure we can now compare across data sets. Okay. Sorry, I think I was saying covariance there. Once we scale it, it's no longer that we've scaled the covariance. We now kind of call this our correlation coefficient. So for the majority of the semester, we won't worry about the covariance other than we need it to calculate the correlation coefficient. We're going to focus on that correlation coefficient because I could now compare the relationship between class size and mass scores to the relationship between height and weight, or the relationship between the money put into research and development and the number of units I sell as a firm. Okay, so we've got this correlation coefficient that's going to be a little more useful than that covariance would be. So another kind of, and we won't go through all of the mathematical proof as to why, although you can kind of envision where this is coming from. So I've got like the deviation, standard deviations would be the deviation squared and then taking the square root. We could do a bunch of math and kind of prove that that correlation coefficient, at most, the strongest relationship would be 1, right? And the strongest negative relationship will be negative. So we know that it's going to be somewhere because we've scaled it by the standard deviations. If we actually work through the math, we don't want to. It's not overly exciting, but we know it'll always be between 1 and -1. 1 representing the strongest positive relationship, -1 representing the strongest negative relationship. If I have a correlation coefficient of 0, what is that telling me? These two variables are unrelated. They're not related at all, right? And we can see any value in between. Right? I can see 0.5, -0.3, whatever. Okay. So kind of walk through that covariance example. Oh, before we go to Stata, because I am going to probably show you this. It's not quite correct. We'll add on to things that we're talking about to get a better measure of this. So what I'm saying right now is not theoretically, technically correct, but for the sake of where we're at, it's easier to think about it this way. If I were to take every observation I have in my data set, every combination of that X and Y variable, so maybe every combination of class size and math scores, which is what I think I have. Well, so this is going to be my class size. Here's my math scores. I can visually kind of imagine, what do you think the correlation coefficient between these two variables are? Well, if I just looked at every single data point plotted, it looks like that as class size goes up, what's happening to my math scores? If I had to kind of draw a line that best fit this data, it's not the strongest, but it looks like it's kind of increasing a little bit. So if I had to guess without calculating it, I probably think that this correlation coefficient is likely going to be positive. Okay? If I had a different scatter plot of this data, so let's say I'm looking at something like this. So I don't know, maybe this is your exam score and the number of beers you drink over the weekend, right? So if I start to plot every single student's combination here, I end up with this scatter plot. It looks like as you consume more beer in the weekend, what's happening to your exam score? We have a negative correlation coefficient there, right? So this line that best fits the data, you can think about is like its slope represents the correlation coefficient to you. It's not technically quite correct, but for now, that's a good way to think about it, okay? So how do we get some of this stuff from Stata? How do we kind of familiarize? I want to get some practice doing this, okay? So we'll leave off here at this conditional distribution point. I've got kind of Stata open, right? So how did I do this? I went to 1.iu. This is a reminder. Hopefully, you've kind of authorized that cloud storage so that you can access your IU OneDrive. And it's worth mentioning again, if you're using this Citrix workspace, if it's from a web browser, or even if it's from your own device, like you've actually downloaded the program I mentioned on a tablet, you can't actually use the web browser. You have to download the app or the Citrix onto your device. You still can only open and save files to your OneDrive. Okay, so that's why we had to turn that cloud storage on. We then kind of go to IU Anywhere. And there's a step I forgot to show you, and you don't always have to do it. It's just that for some devices, in order to activate Citrix, you'll need to. But if you go to this little gear at the top right, and you go to account settings, sometimes you'll have to activate Citrix. So you'll see, I'm not even going to click on this, and it'll already work for me on this device. For some devices, you'll actually have to click this activate device. And then once we go back, in fact, even if I don't need to, excuse me, and I click on it, and I run this. Oh, yeah. So this one won't let me add it to this computer because I don't have admin rights to it. You would have, obviously, admin rights to your own device. So if I then go back to apps, or like I said, last class, I would star this app so that it just shows up on my homepage, just a little bit easier to find. And then I go to open. That's what opened up kind of Stata for me. Okay. So once I'm here, I said there's likely 3 windows we're going to have open. Now I said there's 3. Really, we only necessarily need 2. The third one just kind of helps us take a look at the data to make sure what code we're running is doing what we actually think it's doing. Okay. So I'm going to click on this new do file editor over here, and it opens up a blank document. Okay. So the file that I gave you on Canvas that you should have downloaded and then put onto your OneDrive in whatever folder you're kind of using. So here's my folder. Is that review of statistics do file. Okay. So I'm going to click on that, open it up. I now have all this code. Okay. So we talked a little bit last class. How did I kind of get this? All this does is open a file up. So if I go back to the program and I go to file, the data set I gave you was not in Stata format. It was a CSV file. Right? After this first week, all the data sets I'll give you will always be in a .dta or will be a Stata file already. So you should just be able to go to file open. But even if it wasn't, and you have to go to import, okay, I've got a CSV file I want to open up in Stata. I'm going to find that on my OneDrive. Right? So I go to the folder where I dragged and dropped this onto. This is that state cigarette text file I gave you on Canvas. I'm going to go to open this up. Now here's where sometimes visually, I'm going to drag this up here because there's an OK button at the bottom, right? So I hit OK. Now I can do all this from the interface, but it now spits out at me what the code that it actually had to use was. So you don't have to be a coding expert or remember the syntax always of exactly how I would open up a CSV. I can always do that from the interface up here. But then if I want to run that again, I can copy this code, go back over to my do file, paste it, right? So I've now got, okay, well, this is a problem, right? If I'm working in a small window, it kind of has to drop things down by a line, and it kind of uses these little carrots. So I need to make sure that I'm getting this so that it's all on one line. You'll kind of notice, okay, now it's treating this as text. That's actually the code that I need, okay? So here's that code that you would need. If you ever exit out of Stata, everything you see here goes away. You can't save it, right? You might say, well, look, I can go to File, Save. What you're actually, the only thing you can save in Stata in terms of from the actual program is the data set you're using. If you want to save your code, right, from that do file, you actually need to save that do file, right, under your do file editor. So anything I type into Stata just goes away when I close it out. But anything I put in this do file, I can save this for later use, right? So here, if I run that same line of code, if I can get this to, there we go. Nope. Oh, come on. So if I highlight that and I try to use this little execute button, the little play button here, whatever I've highlighted, it's just going to run that code. The problem is when I first open up data sets, it doesn't have the correct syntax. So when I start out, it can open things up because there's no data that's currently open. We have to add some things to our code, which is if I want to open up a new data set or even the same one, I've got to clear out whatever I previously had. So in some of these homework assignments, you'll be using multiple data sets. You're always going to need to add on, whether or not you go to File, Open, and open a Stata data file, or if you're importing a CSV, you need to add on to the end, comma, clear. In fact, I would just always add this, even if it's the first time you open Stata. That way you know I always need to just be clearing out whatever data set existed before. So now if I try to run that exact same line of code, but I have that clear command, it'll get rid of the old data and open this new data set up. So if I go to execute that, I go back to the program. Sure enough, now it runs. Now when I go to this little magnifying glass grid line, that was the third thing I said you'll often want to have open, I can now see, okay, I've actually got the data uploaded, right? Every observation represents a state in a specific year. I've got the taxes as a percent. So I've got taxes per pack. I've got the cost per pack of cigarettes. I have all these different variables for every single one of these state year combinations. So I've got my data set opened up. I've got all these different variables. I can now start to do things like calculate the mean, the variance, et cetera, okay? Any questions on anything up to this point? Are we having any issues that I can maybe try to help troubleshoot real quick?
I'm not able to open the file. It just sees that there's restrictions.
Yeah, so have you dragged and dropped those files onto your OneDrive? So if you've downloaded them from Canvas and they're on your computer, you can't open those. You have to download them. They'll go to your downloads folder or wherever, and then you have to drag and drop them onto OneDrive. If it's still not granting you access, you likely didn't do the step where you authorize cloud storage correctly, which I didn't go through today, but I went through on Tuesday, right? So I can kind of help you with that today. We'll try to get out of here a little bit early, and I can try to help people kind of at the end of class. But once we have this kind of data set open, once we get it onto our OneDrive and we've granted IU Anywhere access to that OneDrive, this code I can guarantee you will work, right? And this is, I'm giving you in that do file, so you don't have to worry about typing this in or reproducing it. I'm going to give you these do files ahead of time. So all you should have to do, now this is where it gets a little bit different. I'll kind of come down here. So you'll notice like my file paths. This is going to be for my device. These will look different for you, right? You don't have the same folders I do. So just for we'll skip ahead a little bit, right? But if I wanted to open this file up and you try to run the code I gave you, it won't work because it's trying to access folders that you might not have created. These are the folders I have on my OneDrive. So an easier way to do this and how I'll typically put this code into, this is just to start out. I'm kind of showing you. Moving forward, what I will do is give you something that looks like this right here. So we're all going to be trying to open the same .dta file. So in order to create that, since all I gave you was a CSV file, when we import that data, and then we verify that we had the data set open, I'll come back to this. We can manipulate it. But I said the only thing you can do in Stata is save actual data files from the program. In the do file editor, you can save your do file. The actual data you save using just kind of under the program, going to file save as. Right? So I'm going to save as, and I've already got one written here, but I can write over it. So I'm going to save this data set as a state cigarette tax, and then it should automate to a .dta. So this is just like if you were saving an Excel file, it saves it as an XLSX or whatever it is. I'm saving this as a Stata data file, okay? So anytime you import data, you can always save it as a Stata data file. Now, throughout the semester, I'm giving you these all in Stata format already, so you won't have to worry about this. But if you get interested or you want to start a project of your own, if you can go out and get data. So I just talked with a student who I had last semester who's wanting to do something on play-by-play NFL data and quarterback mobility and success of the offense or something like that. He found all of this data that's in CSV format. Well, he can download that data and then save it as a Stata data file. So that's what I'm going to do here. I'm just going to save this. If it already exists, it'll ask me to replace it. That's fine, right? I'm kind of writing over it's the same thing. So I'm going to hit save here. Oh, what is it? Okay. It rewrote over. It's just letting me know you had the same file. I'm rewriting over it. That's fine, right? So once I have that in this .dta format, well, now I can kind of do things like just open that up, and now I don't have to import it. I'm just using that data. So if I go up here to file open, the only thing I can open using file open, right, is I can only open a .dta file, a Stata data file. I can't open up CSV files, Excel files, etc. I can import those and then save them as Stata data files, but I can only go to file open. I can only open up Stata data files. So we had this one, where did I save it? We were just looking at it. Why did it get, there we go. So it's that state cigarette tax file. Okay. So I'm going to open that up. I don't want to save the old data. I just want to restart. So this line of code opened up that state data file. I can verify that by, sure enough, it opened up that state cigarette tax file. Okay. Now I could copy and paste this over, which is what I did ahead of class, right? But I should now be able to always run this kind of same line of code. Switch over here. It'll run it again, and sure enough, it reopened that data set. Okay. So the code that I'm giving you here in the do file, you can always kind of run. With the exception of, if you try to do this, it's going to give you an error because you don't have these folders on your OneDrive. So this is kind of saying, look at my OneDrive, look into these folders. So what I'll do week to week is instead of like usually having all of this, I'm going to give you a data file that's already in Stata format, like this state cigarette tax. I would upload to Canvas this .dta. You'll download that, put it in your OneDrive. You can't use the code that I have in this do file because your subfolders and things might be different than mine. So what we're going to do is use this global path kind of command where we put global, we're going to call this path, and then wherever you're storing your OneDrive files, that's what you're going to put right here. So an easy way to kind of find this, if you go to your Files tab, once you have OneDrive open, and I'll just kind of change this to show you. This computer doesn't take forever to... We're waiting. Got the spinning wheel of death here. Hopefully this opens up here in the next 10, 15 seconds. There we go. So let's say instead I was using my old files from 2025, right? So I click here, I go to my 371 course, I go to week 1. Let's say I actually want to open that state cigarette tax from an old folder. So once I have identified it, right, what I can do is I can go up here, and this looks a little bit different on a Mac, but wherever it kind of shows you all the folders that you're in, I think on a Mac you click Command and then click on it, and it'll show you kind of a similar thing as what I have up here on a Windows toolbar, right? But this is basically your file path, right? This is where all of these all of these files, the folder they're stored in. So I'm just going to copy this. I use Control-C, or you can right-click and copy, or like I said, I think on a Mac it's Command, and you click, and then you have a copy option. So I'm going to copy that. And instead, I'm going to set my global path not to my current semester, but to this old folder I have. So for you, this would be whatever folders you've created. So you don't have to match mine. You could actually just have all your files in something called, for example, if I were you, I would create one folder on your OneDrive and call it, E371 files. Just drag all the DTA file, all the data files I give you throughout the whole semester into this one folder. That way your file path will never change, right? You can always keep using the same. If you start to use subfolders, every assignment, every class, you're going to have to update what that file path is, right? So I break this down week by week, which makes my life a little bit harder because then I have to go in and change my path every single time. If you just drag and drop all of this course's materials into the same one folder, your file path doesn't change for any assignment, for any class period that we're working with. Just always kind of create one folder that you drag every file for Stata for this class into on your OneDrive. Is that making sense what I'm saying here? I know this is all new. I know this is, this is not even my forte in terms of all this technical stuff. I'm much better at just using the program in terms of kind of getting this to work on separate devices. This takes a little bit of time. So don't feel worried if this is seems very foreign to you. It probably should. Okay. So I'm showing you an example where I copied my file path. Maybe yours is as simple as this. And it might not look like this. It might look very different. So if you're operating this off of a web browser, this is going to be like something really long where it says like users, your username, IU username, and a bunch of different stuff. And then it will have the folders you've created. So just because it doesn't look like mine, don't worry. As long as you find where you put that file in your OneDrive, that file path should work. So I'm now going to set this global variable, which is the word path, wherever I put this file. So when I copy and paste that, notice it's not red, right? So this doesn't know how to treat this. So when I put it in quotation marks, it's able to read this as like letters and actually find the correct folders. So even if I copy and paste my file path, I'm then going to need to put these parentheses around it, right? And then once I have that, now you'll notice, okay, I kind of look similar to what I was doing before. Now, if I set my global, and instead of actually putting in that whole file path, every single file that I want to open, if it's always in the same folder, I can just put $, kind of, I don't know, these squiggly parentheses, right? And then that path word, and it will put in where that file exists and then the name of that file. So we had that state cigarette tax file, and it was within all of these subfolders, right? So what this will now do, if I highlight this, it should open up that state cigarette tax variable file. So now if I go back to the program, it's like, okay, it's using this. Well, sure enough, it opened it up, right? And when you've set your path to whatever your iDrive folder is, it'll be able to open up that file that you've dragged and dropped into there, just like I'm pulling it open from my OneDrive. Okay. So this is what it'll look like kind of every week. I'll give you these .dta files. You'll drop them into your ECON 371 folder, and then I'll have a line of code that'll look like this, where you have to change what your path is, but that should be the same every single week, as long as you just created this one folder. And then all of my subsequent commands will use that variable, that word path, so that it's pulling it from your specific OneDrive. Okay. Any questions on this before we keep moving? So once again, I know this is a lot. If we're having difficulties with this, this is where my additional office hours, which I'll post in the Canvas announcement tomorrow, and then next week, make sure we can kind of get this ironed out so you can start working on this first problem set. Once again, even though I'm posting it later today, we haven't covered all the material yet, okay? So I'll then kind of just walk you through a couple of the commands that we can start to use. So one thing that I'm going to do just right off the bat with this data set is I've got a bunch of different years here. Well, if I want to know what the average pack of cigarettes are across every state, what do you think's happened to the average pack of cigarette price over time? Just like everything else, the prices went up, right? So I just want to look at one specific year. So we have this kind of command that says keep the observations only if this statement is true. Now, what this statement is it's saying, okay, look, if I'm looking at the data, I have this variable of year. So if this variable year is equal to 2000, I just want to keep those observations. So hopefully what I should end up with is 50 observations, right? Every single state just from that year of 2000. Right? Now, you might be questioning, well, why did I put two equal signs? That's just the syntax of Stata. Anytime we want to kind of set something where we say, do this if this is true, we use double equal signs. I don't know why it was coded that way. There's likely a good reason that is like much more technical, like on the back side of how the program works than even what I understand, but that's just our coding syntax. It just be the same as like, why do we put, why does, when we use Q's in the English language, why is it usually followed with a U? It is the way it is, right? That's the language. This is our coding language. We have to use two equal signs here. So once again, if I highlight that line of code, I then run it. Notice what just happened to my data set. It only kept the observations that had the year 2000. Oh, we don't have 50 because what? DC, District of Columbia, is in here as well. Okay. So I now have just right? And this is a problem. We don't like to use this keep command very often because it just dropped every observation. My data set, if I were to save it now, I don't want to because it's going to only save just those year 2000 observations. All the old data is gone. So we generally don't like to use this keep command because it gets rid of a bunch of data that we might want to use down the road. Okay? But I'm just showing you here so that we're only looking at one variable so that we can then think about how do I calculate means, medians, modes of different variables. Right? Well, I've got some code in here. I just want to kind of make the point. Stata is pretty user-friendly, but for the sake of what we're doing, it's going to be a small amount enough code that we probably can just get used to the coding, and we don't have to be as familiarized with this interface up here. Anything we do when we type in code can likely also be done using these tabs. So for instance, if I go to statistics, holy cow, I got spatial autoregressive models. What the hell are those, right? So I've got all these different options, right? All we want to do is look at summary and descriptive statistics. I just want to look at the summary statistics of a specific variable. So I could click on that. It then tells me all the variables that exist in this data set. Maybe I want to look at the cost per pack. I then hit OK. Hit OK. Now notice it gives me the code that does that. So I don't have to remember what it is from memory. I can always use this kind of drop-down method, and then I can just copy and paste that code into my do file so I remember exactly what it was later on. But there's also a lot of shorthand that makes life easier. So for instance, that summarize command, I can just use sum, right? And so usually I'll be giving you the code already, and I say usually, I'll always be giving you the code already in these do files, but everything that I put in that do file, there is a way you could find it from that toolbar or that interface, okay? But once again, we won't be doing anything too crazy with the coding. And honest to God, sometimes this interface gets more confusing than the actual code. Just because there's so many drop downs and you're not really sure exactly what options are doing what. So I would primarily just focus on whatever code I'm giving you. I'll never ask you to reproduce anything that's, maybe different variables, but nothing that's any different from that. Okay. So here, once I kept only those observations from the year 2000, if I use this sum command or the summarize command, it'll give me a summary statistics for this variable. So I'm going to do state tax. So in the year 2000, what was the average state tax on a pack of cigarettes? Almost 42 cents. Right? Tax was in terms of US dollars, and so it was about 42 cents. So it'll give me my mean, it'll give me my standard deviation, and it tells me the minimum and maximum. So some state has a tax of what? 2.5 cents, right? And some state has $1.11 tax in the year 2000. Okay. Any questions on anything up to this point? So we can start to see, we don't have to, I have 50 states here. Imagine if I had every student at IU and I had what their GPA was, and I wanted to calculate the mean. By hand, that would take me forever, right? But using Stata, if I have that data, I have one simple line of code, sum this variable, sum GPA. It can calculate the mean, standard deviation, tell me the min and max, just like that, right? This is the power of programs that can actually access and work with data, right? We can do things so much quicker than if we could do this by hand, okay? Now, another kind of nice option we can add into that sum command, and this is where you might have to hunt around. It's not always quite clear from the interface where this would be, but if I give you the code, it's a lot easier just to mimic it. So if I put sum, whatever variable I want to summarize, and then I put comma detail, it'll give me not only the mean, the median, the min, and the max, it gives me a bunch of other statistics. So it tells me the standard deviation, the variance, the skewness, the kurtosis. It even breaks this down into percentiles, right? So it gives me a lot of additional information, and it does it very quickly, okay? So this is, all the statistics that we talked about up to this point. I just calculated all of them within seconds using Stata, right? This is the power of this program, right? Or other programs like it, okay? Another thing I'll mention, I might have mentioned this last class, and I often will do this in the do files I give to you. So here's the line of code that we were actually running. Anytime you see this green text, right? I created this by using these double backslashes. This is essentially going to be comments that I want to add in that isn't Stata code. So what Stata does is when it sees these, it just ignores them. It knows it's not code. It knows it's just a statement you're putting in there, so that if you were looking at it, okay, if I'm looking at this for the first time, what the hell does sum state tax comma detail do? Well, I'm telling you in this do file, I added what we would call a comment. It calculates or provides the median, the variance, the skewness, and kurtosis, in addition to the original summary statistics of the mean and the standard, et cetera. Okay. So I put these comments in the do files so that when you're looking at it, it's a kind of a reminder, and we talked through it in class, But when you go back, it's like, oh yeah, this is what this line of code is doing. I'm not just giving you the code and like, hopefully you remember or have to go back and look at your note. I'm giving you comments that remind you of what we were doing with this line of code. Does that make sense? That should hopefully help when you're kind of going back and revisiting outside of class. Okay. Where are we at on time? Okay. So a couple other things I want to kind of point out before we get out of here today. So even though it provides me with those summary statistics, I can't actually like use them. So let's say I wanted to take the mean and I wanted to multiply it by, I don't know, the population of that state. You know, I don't know why I want to do that, but let's just say I want to do that. Well, there's no variable that I've created that is equal to that mean, right? So one thing that we can do is if instead I want to create a mean and then like multiply it by the population of a state, I don't think I have the population of the state in this data set, but let's just assume I did. I could create a variable that is equal to the value of that variable's mean. So in this class, if you look at outside help sources or you were to do this from the drop-down interface, this gen command, often what that does is it's going to generate a new variable. Now, you can do things like generate a new variable equal to 1. So what that's going to do is it's going to create a variable, and it's just going to be 1 for every observation. So I'm going to run this line of code. This is where sometimes I'll add things in the class, which is where it's helpful to have the do file opened up as I kind of add things in, right? If you're not able to do that today or we haven't gotten state working, you can always kind of write this down in a Word document and copy and paste it in your do file later on, right? Nothing we're doing here isn't anything that we couldn't just type out in Word. So that's a good way. If you can't get your do file editor to work in any given class period, you can always kind of write down what I'm doing in terms of lines of code into a Word document and then copy and paste it later. Okay. So if I run this code, if I can get, man, the Wi-Fi must be terrible here. So I'm going to look at this data set. I've created a variable and it's just equal to 1 for every single observation. Not very interesting, not very useful, right? The difference between gen and egen is when I use egen, it's using some built-in functions in Stata, right? So if I tried to just use gen here, and I want to create a new variable, which is the state cigarette tax mean. So this is what I'm calling the variable. Before I called it variable 1 or var1. I want to set this variable equal to not the value of 1, but the mean of that state cigarette tax variable. Well, if I try to use just gen, it should give me an error because it doesn't know what mean is. I need to use this egen, which is then able to access different built-in functions that are in Stata. So I would say if you're ever doing anything in Stata, just default to using egen, right? Because that's going to give you access to not just creating general variables, but accessing all these built-in programs like the mean. So what does the mean program tell Stata to do? It tells it to go through every observation, add all those values up, and then divide by the number of observations we have. Instead of having to type out that formula, there's already a built-in program that does that. So here, if I use the egen function, I can very quickly create a variable. So that code ran. I now have a variable that is equal to the state cigarette tax. If I then wanted to multiply that by the population, if I had a population data or variable here, well then what could I do? I'm going to just generate a new variable and it would be equal to population times whatever the state tax mean variable I created is. Once I create that variable, I can then use it to do different calculations. Now we don't have the population variable here, but I'm just kind of using that as a hypothetical kind of thought experiment. I can also do things like create a variable that's equal to the median, right? When I was using that sum command, it just displayed to me what that mean and median were. It wasn't saving them anywhere, right? So that's where if I'm asking you to kind of calculate that mean and median, the sum command is great, and you could write that down like for the first problem set, but if you ever want to access it later, if you haven't saved it as a new variable, it's going to go away, right? If I save it as a new variable and then save that data set, I now will always have that variable in that data set when I go back and open it back up, okay? So we could do things like create the median of state cigarette tax, create the standard deviation, right? Instead of doing this by hand, does it very quickly for us in Stata. I now can tell you the mean, the median, and the standard deviation of that state cigarette tax very quickly. Okay. Also, I was showing you a scatter plot earlier. There's some kind of, and we won't utilize them a ton in this class after this first assignment, but there's a bunch of interesting like graphics you can create in Stata, not really the primary focus of this class. That would probably be like a data visualization course or something like that. But just kind of starting out because we mentioned it today, there is a scatter plot that you can create, and this is going to be the code. So all you do is, here's how I can create a scatter plot for any two variables. So if I wanted to know what's the relationship between the cost per pack and state cigarette taxes, if we're good at basic introductory economics, if the tax is higher, what's going to happen to the price? It's going to go up, right? So if I look at this scatter plot, what correlation coefficient would I think exists between these two variables? Positive, right? So I kind of go ahead, I run this. This can take a little bit of time, especially if we're operating kind of from Citrix and our Wi-Fi is not great. But it'll create a scatter plot. Sure enough, wow, that's like a nice linear line between tax and cost, or tax and price. That's what we would expect to see using our very basic, microeconomic theory. Okay. I could really do any two variables. So if I take a look at this here, I don't know, what other variables? So I could do like tax revenue. So here, maybe this one's a little bit trickier. So let's say I want to look at that scatter plot of tax revenue and state cigarette taxes. Well, when I increase taxes, I know the price goes up. But if the price goes up, what do I also know? The amount purchased is going to go down. So I don't really know what's happening to total revenues. It would depend on getting some real basic Econ 101 review here today. The demands elasticity, right? So I could actually kind of determine whether or not we're on the elastic or inelastic portion. Okay, well, it's not quite clear. It looks like maybe there's a positive correlation here, but it's kind of floating around zero there. It's kind of hard to say, right? But this is how we can create scatter plots really for any two variables that we wanted, okay? And then we talked about the correlation coefficient today. I don't have to just kind of eyeball this line of best fit. I can actually calculate the correlation coefficient by using this correlate command. And this tells me the actual correlation coefficient between tax and cost per pack. I could do the same for any two variables, right? Now it gets to be this, I don't know why it does this way. Like it shows me the correlation coefficient. What should the correlation coefficient be between a variable and itself? Well, they're always the same value, so it should be perfect correlation or correlation of 1, right? So these diagonals tell us the correlation coefficient of a variable itself. It's not useful, right? But the thing that we were wanting was that correlation coefficient between tax per pack and cost per pack. And we'll look a little bit more next week. The reason why it displays it this way is because we don't have to just look at the correlation. We can also look at the covariance, in which case these won't always be 1. Okay. So just a kind of quick introduction to how we start to look at these very basic statistics and data. Once again, I'm trying to start out slow. There's many questions. Like if you've got questions, I can't stress enough. Get to me early on this week or next week to get these kind of stated questions out of the way and make sure we can all be using it, because we're going to just keep on moving next week. Okay. Next week, we'll talk about how we standardize variables. So this is going to use some of the things that we talked about today, the mean, the standard deviation. We'll talk a little bit more about distributions, but we want to make sure that we can open, save Stata data files, import like these CSV files I gave you this week, and then save and open our do files in that do file editor. Okay. If you have some questions, a little bit of time here, I can try to kind of troubleshoot and help you as much as I can. If I'm not, I'll reach out to the tech department, which I've already done for a few of you. All right. Have a fun, safe weekend, and I will see you guys on Tuesday.